This episode is supported by MonsterJoysticks.com. Level up your Raspberry Pi with our all-in-one arcade kit using genuine Sanwa arcade parts. And OneClickPrint.com for your photos on canvas, acrylic, gifts and more. Local craftsmen and global delivery.
We've recently been exploring the story of the UK's computer literacy project in the 80s, why it came into being, how it was executed, and the microcomputer that was selected for the project, the BBC Micro, and a fascinating story it is too. Who better then to help us fill in the gaps and expand on what we've learned so far than our guest today, who is one of the designers of the BBC Micro itself, as well as the ARM CPU, which we'll also discuss. Welcome to the cave, Steve Furber. Welcome, Steve.
Hello, I'm glad to be here.
Acorn computers and your work with them goes back into the 1970s. So how did you become involved with Acorn?
My involvement with Acorn actually goes right back to the start of the company. I was a student at Cambridge and in the late 70s I was doing a PhD and then a research fellowship. And I was increasingly interested in the idea of building some sort of flight simulator. I've been keen on flying through my youth. And I heard about a bunch of people who were planning to start a new student society called the Cambridge University Processor Group. And this was just a student club for people who built computers for fun. And I wasn't a founder of this club, but I joined it from its outset. And not long into that, after we'd hand-built a few machines, Herman Hauser approached me saying that he and Chris Curry were thinking of starting a new company in the microprocessor business, and they'd come to the processor group to look for likely recruits to help with the technical side. At that time, when they formed the company, it was called CPU Limited, which stood for Cambridge Processor Unit Limited. One of the earliest jobs I did was hand build a prototype of the Science of Cambridge MK14, because Chris Curry was still linked with that. And then Sophie Wilson looked at the MK14 and in her normal style said, "Yeah, I can do better than that," and went home and designed a little hobbyist home computer that was marketed under the Acorn name, the Acorn System 1. So Acorn was originally a trading name for CPU Limited. And I was still at the university. My day job was aerodynamic research, but I built little bits of computer stuff for Acorn, and they fed me with components, and I turned them into something useful. So I was kind of doing a bit of design on the side.
So it was a fairly informal relationship to begin with. And the work that you were doing at uni, was that your inroad to, you mentioned you liked flight simulators, which I'm a big fan of. So is that how you got, because there can't have been many flight simulators around at the time. So is it through that work that you had access to some?
Well, that generated my interest in computers, and then I got involved in CUPG and Acorn, and effectively my focus turned to the computer itself. Of course, my interest was closed full circle when the Aviator game came out on the BBC Micro, which was my big favourite.
On the shelf behind me there, yes.
Sure you do. That was great, and I really felt that was closure on the flight simulator.
It seems to be quite a common thing, because I know Jay Miner, who was the engineer behind the Amiga and some of the Atari computers, put specific functions into the Amiga, like the ham, the hold and modify mode, because he was a flight sim fan, and it would help with that. So you have something in common with him there. So the company's first contract, I understand, was to create fruit machine controllers. Was that something that you had any involvement with?
Yes, indeed. We were one of the first companies to think about how you could replace all the electromechanical control circuits that were then used in fruit machines with microprocessor controlled things. And we developed a dual processor system based on the NatSemi SCAMP chip. And I think I mainly did software on that. I clearly remember Sophie was also involved, and one of the big problems at the time was the newfangled electronic fruit machines were a bit easy to crash if you flicked an electronic cigarette lighter near the cash slot, they would sometimes pay out. and Sophie developed an FM radio receiver that detected any attempt at electrical interference and immediately shut the machine down. So that the one thing you could be sure it would not do was pay out. And I also remember these were tested by plugging into one of those block mains adapters with multi-plugs and plugging the fruit machine into one socket and an arc welding transformer into the other, and checking that arc welding from the same main socket didn't disturb the fruit machine.
Can you remember any other markets? You obviously had the fruit machine market. What other markets were Acorn aiming at then? Because the consumer computer market, the home computer market, wasn't really a thing, or it was sort of in its infancy at this point. So who were the products aimed at, such as the System 1 or the System 14 that you were working on?
Well, the
MK14, sorry,
was the Science of Cambridge product. Science of Cambridge was the company that Chris Curry had set up with Clive Sinclair. So that was a different company, and my involvement in that was just hand prototyping the first version, I think. Acorn very rapidly developed the System 1, which was sold as a kit. So it was intended for hobbyists who knew which end to pick up a soldering iron, which is a lesson you have to learn. But it was based on standard Eurocard format, and the company then moved in the direction of developing accompanying cards to the same bus interface. And so there were the series of Acorn systems that came in standard Eurocard rack format, where you could add disk controller and VDU boards and so on, and floppy disks even. And these were sold, I think, in fairly modest numbers as basically small industrial control boxes.
Right. Okay.
So that was the market, and then from that, and observing the external market, Chris Curry led an activity to develop the Atom, which I didn't have a direct involvement in. And then the next machine after the Atom was the BBC Micro.
Yeah, so the Atom was 1980, the same year that Sinclair released the ZX80 computer. It was a low-cost machine, and Acorn's first really targeting the casual home market specifically.
Not very casual initially, because again, it was sold kit. And there were a number of stories about how these kits went wrong. The one I remember is the customer who understood that heat was bad for chips, and so he very carefully glued all the chips in the circuit board. But it still didn't work.
What a surprise.
I think at this point, Acorn began to realize that the market was growing larger than the number of people who did know which end to pick up a soldering iron, and effectively the Atom started being fully assembled, sold fully assembled, and I think that was the style for Acorn from that on.
Were you aware of any resistance to moving into the home market from within the company?
I don't think so. The company was very small at the time. I mean, I finally joined as a full-time employee in October '81. So the BBC contract was sorted out by then. I had a fair hand in the design of the machine, but I didn't join full-time till October. And I think at that time the company was still only 20 to 30 people.
Right. Okay. So any objections could be sounded out in the pub, really, around a table.
I think anything we could do that looked like it might sell something was deemed a good idea.
So that's the Atom, and then you mentioned that the BBC Micro was next. How forward-thinking was Acorn at the time? For example, was the successor to the Atom already being devised when the Atom was launched, or were they just waiting to see how the Atom performed?
I think the Atom went out as it was. A number of us had a few qualms about the way the Atom had been put together. I think my biggest qualm was that it used the chip that generated a 60 hertz frame rate video output, which of course most UK TVs did not cope with at all well at that time, being based on a 50 hertz frame rate. Well, I don't think there was a successor planned at the time. I think when that went out and looked like it was working reasonably well in the marketplace, then we started to think about what was coming next. And already at that point, it was clear that the 8-bit micro did not have a lot of life left in it. And so we were developing this proton architecture, which used a sort of 8-bit micro to do all the fiddly bits at the front, but then allowed a bigger 16-bit microprocessor to be coupled to it as a dual processor system.
Okay, can you remember which 16-bit processor you were planning on using, or was it something you were going to develop in-house?
Oh, there were certainly no thoughts of developing in-house at that stage, and I don't think we had anything specific in mind. There were a number appearing on the market at that point, but this thinking had not advanced very far by the time the BBC issue came up.
Right.
And when the BBC contract became a possibility, very rapidly the front end of this dual processor was sawn off and turned into a potential prototype for the BBC Micro.
So as we come into the BBC Micro then, the mood was set by TV programs such as, I don't know if you're aware of Horizons, Now the Chips Are Down, and the Mighty Micro. This is in the late 70s, really, into the early 80s, which suggested that we as a nation were falling behind the times and needed to address the risks and challenges of automation and computers taking our jobs. Is the sentiment that we were reaching a crisis point something that you shared at the time?
I don't remember thinking it was a crisis point. I remember thinking it was an opportunity. I think the microprocessor basically moved the cost of building a computer into the territory where everybody could potentially own one. Up to that point, computers had been big, expensive machines run by men in white coats, and now suddenly everybody could get access to one, and this created very large opportunities. I mean, nobody imagined how large they were, but they were clearly big.
But there must have been a sense of excitement. You must have had that feeling that you were in the right place at the right time.
Oh yes. And it was a very exciting time. I heard somewhere that there were several hundred small companies in the UK all designing personal computers at the same time. Because it was very cheap. You bought the chips off the shelf. You configured a circuit board, which didn't cost a fortune, put it in a plastic case, gave it a fancy name, and then you'd see if anybody would buy it.
Yes, yeah. Just to the left of me, I've got an Auric 1 and a Dragon 32 and all of these other machines that just came and disappeared as quickly as they arrived. Yeah. Yes.
I mean, the market was wide open for the enthusiasts, for the hobbyists. I mean, I think we still didn't foresee that it would really get into every home or every classroom, but it was clearly a big market relative to the scale of the company at the time.
Mm-hmm. So then the BBC came knocking with this opportunity. Tell us about the process of preparing the prototype, because you had a presentation to give, didn't you, to try and convince the BBC?
Well, the company did a number of things, and I wasn't involved in all of them, and I don't know what they all were. But I do know that with about a week's notice, we embarked upon the challenge of trying to build an electrical prototype of the hardware. And in parallel, Alan Boothroyd, who was Acorn's industrial design consultant at the time, built a model of the case so that when the BBC came on the Friday, we could say, this is what it'll look like and that is how it will work. And we turned all that over in about a week. And there's the legendary story of Herman playing Sophie and me off against each other by saying the BBC are coming on Friday, can we show them a prototype? And Sophie saying, don't be silly. And then Herman ringing me and saying, well, Sophie thinks we can do it. And then Sophie back and saying, well, Steve thinks we can do it. I mean, again, I was not. This was before I was a full-time company employee. So
Sure. So were you present at the presentation itself, or were you catching up
oh,
on
yeah.
some sleep? You were. Okay.
I think I'd been in the Acorn office pretty much solidly that week, day and night, trying to get this together.
And so you had the physical thing to show them, the case, the computer in there. Was anything coming up on the screen? What could you actually show them within the presentation itself?
By the time they arrived, we had BASIC running on the machine. It took Sophie until the Friday afternoon to get the graphics working. So, I mean, and again, working in a primitive way, in a very, and the BASIC that we demonstrated was effectively Atom BASIC, ported to the new machine, because we didn't have the contract yet, so the negotiations over the spec of BBC BASIC had yet to start.
Sure, yeah. And did you get any kind of inkling of what the guys that came to inspect it thought? Did they give you any feedback on the day?
No.
No? Okay, yeah.
No, we you know, on the technical side, we were very pleased that the thing had finally been coerced into life, you know, early on the Friday morning, in time to have a working system to show them. For most of the week, we hadn't reckoned we'd get that far, so we were happy with ourselves, but we had no idea what the BBC thought of it.
Sure. Well, I've got a few questions throughout here from viewers. So I've got one to put to you here from Arne Schmitz. He says, I think I know the answer to this. Did you see the film Microman, which I'm sure you have? And if so, was it accurate?
So yes, I've seen the film Microman. In fact, I was approached by the production company ahead of its production, as were most of the people involved, and they bought me lunch, and I told them the anecdotes, and they did go around talking to everybody to try and assemble anecdotes. Of course, they got inconsistent stories because it was a long time in the past. But basically, I mean, the good thing about Micromen is they found a nice story. Okay, I think the story of the friction and friendship between Chris Curry and Clive Sinclair, I think, made a very good framework around which to build the story. The technical details were largely right. I mean, the thing I always have to point out is Sam Phillips, who plays me in the film, has a beard. I've never had a beard. In fact, I don't have the right sort of hair for even attempting to grow a beard. It's far too fine. He wore glasses. I didn't need to wear glasses until my mid-40s. And I think the thing that was probably the most upsetting was he chain smoked in the lab, and I have never smoked. But that's a kind of classic media way of portraying times past.
Yes, yeah.
Today, nobody smokes in the lab, and then, well, even in the early 80s, I think it was firmly deprecated.
Yeah. And with regards to the presentation itself of the prototype, it's almost like a bomb defusal scene where they cut the red wire at the last second. Was it that close?
It was not 3 minutes after they arrived. It was 3 hours before they arrived.
That's still very close. Yeah.
It was very close, and you know, yes, it was Herman who came up with the last idea that caused it to leap into life, and of course Herman had really very little idea what was going on technically, so it's a bit annoying that he came up with the final solution. I mean, I think that the fact that they portray this as a bomb disposal exercise, I think that's just entertaining. I mean,
yes.
you've got
and
the Microman is built generally around true anecdotes with a little bit of dramatic effect added to maintain the excitement.
So Acorn were, of course, chosen to supply the machine based on that prototype. Time was limited to get the machine on the shelves. Did you receive requests to change the design after this point, or do you think the tight schedule helped to prevent that final computer really being designed by committee? Did that help?
I think on the hardware side, which is where I was principally involved, the core of the machine was based on a machine I'd built at home the previous year. I built a rack-based system that used the same technique of multiplexing processor and video accesses to a single unified memory. We ran it all twice as fast in the BBC Micro because it was much more tightly integrated onto a single board. So the core of the hardware was very much sustained through the development. There were one or two things that came in as a result of BBC requests. I think the most important for them was the support for the Presto display mode.
Right. This is the Mode 7 teletext mode, is it?
The teletext mode, that's my phrase, yes. Yes, using, I think, the Philips SAA 5050 chip. Is that right? I haven't...
You designed it, sir.
I haven't tried to remember that number for nearly 40 years. So.
And there's also the slot in there for the speech chips. Was that an addition that was requested?
That was also an additional thing brought in, I think, at the BBC's suggestion.
Okay.
So there were things around the periphery that got adjusted, but the core principles of operation didn't change. Were the same as the prototype that we showed them at Easter in '81.
We've had lots of viewers ask this question. Mark, Julian, Abraxas and Greg all ask, were you happy with the final BBC Micro? Was it everything you intended it to be? Or was there anything that you wish you could change about the machine?
Well, I think in general, I was happy with it. I was very nervous. There were hardware components of the machine that I thought were too near the edge. Okay, so I would have liked to have had more time to design it to be more robust. And this did come out if you took it into the Australian desert at 35 degrees C. Things would start to fail. And there were the chips that drove the DRAM. These were NatSemi 81LS95 chips. And other suppliers came with chips with identical specs, which we plugged into those sockets, and they just didn't work. And so clearly we didn't know why they didn't work. And equally, we didn't know why the 81LS95s did work. But something in there had a fairly low tolerance on it. And it's rather surprising that this never came home to roost 1.5 million machines later.
Well, actually, time has shown it to be, at least in the British climate, to be a very reliable machine. Outside of a few capacitors in the power supply, it seemed to be very robust. Yeah,
and this to me is very surprising, but welcome. Of course, the classic story that should have been different is I prototyped the floppy disk interface using the Intel 8271 disk controller. And of course, I read the manual carefully and set up some parameters and tested it and got everything working. And that all seemed fine. 5 years and 1.5 million machines later, people were beginning to get a bit worried about the preponderance of disk error 15 in the field. And this turned out to be because I had got one of the parameters wrong when I built the prototype board. And nobody'd ever checked them properly since. So the disk error 15 thing was all my fault.
Well, you seem to have gotten away with it, Steve, but it's very honest of you to come clean. Paul Jacobson asks, if the prototype wasn't chosen to be the BBC Micro, would it have been released as the Proton as planned, or would you have had to reconsider the design? What do you think would have happened there? I know it's a very big what-if question. But... It's
a big what-if question. I think we would have... The first line we would have taken would be to continue with the development of the Proton as we were thinking about it before the BBC Micro. Now, whether that would have survived through to a marketable machine, I don't know. It may well have ended up significantly too expensive, and therefore it either may not have got into production or it may have failed in the market because of the price. Mm-hmm. But as you say, there are a lot of what-ifs in there.
What-ifs, yeah. And you did try to, or Acorn did try to push the BBC Micro into the international markets. You mentioned Australia, but the USA in particular, where it didn't really take hold over there. Why do you think that was?
Oh, I think there are a number of reasons. And of course, had we been designing a machine for the US market from the outset, then a lot of the BBC's most liked features would have had to go. Okay,
Right.
because the issue with the US market was that to gain FCC approval, you had to plug a meter of cable into every socket, and there were a lot of sockets on the BBC Micro, and then you had to demonstrate that you passed the radiation tests. Okay, having connected all these aerials to the machine to make it radiate as much as possible. So in order to sell the machine in the US, the circuit board inside the case had to be encased itself in steel to provide screening. All of the ribbon cable connectors had to use screened cables, which of course in other markets they didn't. And generally the machine became heavy to carry, I mean noticeably heavy to carry, and expensive. And probably even more fundamentally, of course, we were taking Apple on in their home territory. And that was never really going to work. I think the other thing that was learned from that experience was Acorn tried to do this by setting up its own sales operation in North America. And you'll see that the people involved in Acorn at that time have never done that again. I mean, what companies like ARM have excelled at is using existing sales channels rather than developing their own from scratch. Because it's just too expensive to set up effective sales channels in a market as big as North America.
Mm-hmm. Can you remember a push into any other international markets, any other countries that was perhaps more successful? I think you did okay in Holland, didn't you?
The machine did well, particularly in Australia and New Zealand. That was very successful. Reasonably successful in Holland, I think, in Germany. And for the Indian market, there was actually a clone built under license in India called the Dolphin, I think, which to suit the Indian tastes came in a shiny silver box instead of the cream color. With bright blue keys. So physically it looked like a BBC Micro, but the color scheme was very Indian.
See, just this week I took a BBC Micro to a paint shop to get it color matched and restored. We sprayed it and restored it back to how it looked originally. So I'll have to do another one in silver now.
Yes. The plastic hasn't. Well, particularly if it's out in light, it hasn't survived the 40 years terribly well, has it? It's all yellow.
Yes, it's the same for every Micro, though, that's cream. It's not specific to the BBC Micro. They just sort of go yellow if they've been exposed to the sun and get patchy. Yes. Yeah, I don't think we can hold that against any of your designs.
Well, I wasn't responsible for the case.
So Julian Regal asks, what part of the BBC design are you most proud of from an engineering perspective?
Well, I think the thing I'm most proud of is the intrinsic performance and efficiency we got from the fundamental design of a single memory working quite hard to support both processor and video, and the trade-offs that allowed. I mean, it was a very small memory by today's standards, stupidly small, but you could choose higher quality display, the cost of less space for code and data. There was a very flexible trade-off in that region. So I think the core of the machine was something that I was quite pleased with. And as I say, that's something I'd developed at half the speed on the machine I'd built at home the previous year. So
we'll come back to the legacy of the BBC Micro a little bit later, but I'd like to move on now to the Acorn RISC machine, or the ARM project, the same ARM that's in billions of devices today. Where other micro manufacturers were basing their machines on the Zilog or Motorola processors, why did you feel the need to create your own processor at Acorn?
One of the benefits of the dual processor origins of the BBC Micro was that it was produced with the tube interface. So it was very easy to couple a second processor into it. And that allowed us to play with a whole lot of processors. We built many more second processor boards than were sold. We did sell boards based on the NatSemi 32016, and
I've got a 6502 one here.
The 6502 second processor was my design. There's an entertaining, though very techie story there about metastability, but maybe that's not where we need to go. We also had an 8286 because one of the BBC's original requirements was a Z80. It was something running CPM. Mm-hmm. I think we did that through the second. Maybe it was a Z80 second processor. Anyway, we built 68K ones and so on, and all of these disappointed us. These were 16-bit microcomputers, but they didn't really seem to outperform the 6502, particularly the 4 megahertz 6502 second processor. And we came to the sort of conclusion that the main thing that determined the performance of the machine was how much memory bandwidth the processor can access and use. And standard memory, which was the expensive part of a microcomputer, had a certain performance, and the 16-bit processors of the day could not tap that performance. They were slower than the memory. And we thought this was wrong. The second feature we thought was wrong was a result of their architectural origins really being in the mini computers of the 1970s. They all had very complex instruction sets. And the figure I remember is the NatSemi 32016. One instruction was a memory divide instruction, which took 360 clock cycles to complete. Now, the clock was only 6 megahertz, so that's 60 microseconds. Now, a standard floppy disk, a standard density floppy, gave you a byte every 64 microseconds. A double density one, which was coming then, it was a byte every 32 microseconds. You clearly couldn't handle that with a NatSemi 32016. So the real-time performance of these 16-bit processors was much worse than the real-time performance of the 6502, which we'd exploited fairly mercilessly on the BBC Micro. And so we were scratching our heads about these deficiencies when Herman threw a couple of papers on our desks about the risk work at Berkeley and Stanford in the 1980s. I mean, we must now be talking about 1982, 83, I guess. And, in our minds, designing a microprocessor was something big semiconductor industry did. It was a black art. But here was this postgrad class that had built a competitive microprocessor in a year. So a bunch of inexperienced students. So we thought, well, maybe there's something here we can tinker with. And Sophie started tinkering with a RISC instruction set with a lot of experience of writing basic interpreters and a lot of understanding of high-level languages. Of course, the Berkeley and Stanford examples were academic prototypes. We needed something a bit tighter for commercial use. And Sophie came up with an ISA, which and I produced a microarchitecture for that. And I did tweak a bit the instruction set to make the microarchitecture cleaner. And then there was this formative visit to Phoenix, Arizona, when we went to see the design team who were developing the 65C816, the sort of extended address version of the 6502. And we went expecting to find, large glossy offices of the type you see everywhere in California these days. And in fact, this development was going on in a bungalow in the suburbs of Phoenix. And they were hiring school kids in the summer vacation to do basic cell design and so on. And Sophie and I did come away from that visit with the sense, well, maybe if they can design a microprocessor, so can we. And
you'd pulled back the curtain on the Wizard of Oz.
That's right. And so we went back, and all the time, I mean, this was October 83 when we came back from Phoenix. And of course, it was only 18 months then having the ARM silicon. Throughout that time, we thought this RISC idea is so obvious that industry is going to pick it up and trample all over us. But at least we'll have learned something by the time we get to the end of this process. We'll be wiser for picking a CPU from from the market. But interestingly, industry was strongly resistant to this idea. It was too radical for industry. They were too conservative at that stage. By the late 80s, of course, lots of industry was coming out with RISC processors, but they were actually coming out with RISC processors at the high end, whereas we designed the ARM to be a kind of efficient low-end processor. So it survived.
Yeah. Well, for the development of it, viewer Arn asks, what tools were used back then to design a CPU, and has the process changed much since then?
So that's an interesting question. And the main tool that I used to design the microarchitecture was BBC Basic.
Oh, wow. Wonderful.
And the first ARM reference model was 808 lines of BBC Basic, written very much in RTL style, which a hardware designer will recognize, register transfer style. And I thought that model was lost, but in fact, 15 years ago, I did some garage archaeology and found some floppy disks in the dark recesses of my garage, and on there was the original BBC Basic reference model. So that's now with the Centre for Computer History in Cambridge. So basically, at the functional level, BBC Basic was the tool, and then the little modules in there were described as block specs, we called them. The register bank does this, the ALU does that, the barrel shifter does this. And those were handed to our VLSI design group, who then used much more conventional tools from Compass Design Automation. They were the software side of VLSI technology. And they used their tools to implement the layout. A lot of the ARM1 layout was manual, and some of it was compiled cells, but most of the data path was manually designed. And so it was Compass Design Automation. BBC Basic Compass Design Automation is the direct answer to the question. And has the process changed much since then? It's changed enormously at the front end. So a modern ARM CPU is designed using a high-level hardware description language, typically Verilog, sometimes VHDL. And it's also become probably 100,000 lines of code as opposed to 800. And some of that worries me, because there's a lot of, an 800-line program is something that a single person can understand fully. As 100,000 lines, nobody really knows the whole story. It's all divided across a team, and different people have written different bits. The back-end tools, probably today, of course, nearly all ARM processors are physically designed through synthesis. I suspect there are some that still have quite a lot of human input. For example, I don't know how much Apple optimizes the ARM processors it develops, but they may have things like semi-human data path design and so on. I don't know, but most of the market simply presses the button on the synthesis tool. You've still got lots of controls, and you have to do quite a lot of Pareto optimization to get the processor with the characteristics you're looking for. But there's much less manual back end these days.
So the Acorn Archimedes was the first system that Acorn put out with the ARM chip in there in 1987, I believe.
Yep.
Like the BBC Micro, it became a staple of school classrooms around the country, and that was the case in my upper school in the early 90s, and many new models appeared over the years. This was the same for viewer Chris Appleton, who asks, did the BBC Micro's position in the education market influence the design of the Archimedes? Were you gunning for that educational market again?
Well, clearly Acorn had a position in the education market by the mid-80s. BBC Micro had established that. And if you look at the early Archimedes designs and the A3000, we even retained the orange function keys. And I think some of them were still sold with the BBC.
They were. They had the little owl logo on there, and it was the BBC Archimedes. Yeah.
So that was very much a continuation at the functional level. They all ran BBC Basic. but probably significantly enhanced, but still recognizable. Internally, the hardware was more a reaction to doing the opposite than a continuation of the same. Because, as I say, I was quite nervous about the reliability of the design, and for the Archimedes, we made very sure that that wasn't going to be a problem. The BBC Micro would fail at about 35 degrees. I remember Archimedes systems being in thermal test chambers, running perfectly happily at 120 degrees C.
Oh, wow.
We had to take the floppy disk drive out to stop the floppy disk from melting. But all the electronics in there was really very thoroughly engineered and toleranced. And of course, we'd gone from buying chips and assembling them into a machine to designing the chips around which the machine was built. The BBC Micro did have a couple of semi-custom chips, the video and serial ULAs, and actually the video ULA was the source of significant problems early on. But the Archimedes, the philosophy was we have a 4-chip set, and that covers everything apart from memory and bits of I/O that are too sort of variable and detailed to try to integrate. So it was always a 4-chip set: ARM, MEMC, VIDC, and IOC, and design on silicon was the key approach. That the chips did what we wanted, not what some independent manufacturer some years earlier had decided they should do.
Mm-hmm. I was an Amiga 500 owner at home at the time, but I was always a bit envious of my friend with his Archimedes because it could push all of the 3D programs in particular a lot quicker. It certainly performed very well compared to its peers of the day. Yes,
and I mean, when it came out, I think in performance terms, it was well ahead of anything else on the market. It still had the BBC philosophy of shared memory for processor and video, though handled in a subtly different way. But yes, I mean, we went from 8-bit to 32-bit because that doubled the memory bandwidth, and memory bandwidth was the key thing. The ARM was also quite good at using optimized memory access modes. It has a little signal it produces that tells you if you're likely to be able to use page mode in the DRAM. Things like that were quite highly tuned. So the accessible memory bandwidth in Archimedes was 25 times that in the BBC Micro, I think.
Well, yeah. Well, the computers aside, the Archimedes aside, Acorn set up ARM Holdings in 1990 to exploit the CPU as a technology in itself, and not the computer. We're barely out of the era of luggable portable computers at this stage, but could you already see the potential for ARM specifically in a future of mobile devices outside of desktop computers? Was that clear to you in 1990?
Well, first I should explain that I had left Acorn before ARM Limited was set up. I moved to my current position in the University of Manchester on the 1st of August 1990, and ARM Limited was set up and running by November, but it hadn't even started when I left. And of course it started because Apple approached Acorn and said they wanted to use the ARM in their Newton computer. And Newton was very much, a handheld portable machine. So ARM Limited came into existence because of the Newton. They were pushing an open door when they approached Acorn, because Acorn had basically a flat market in education, and the cost of maintaining a state-of-the-art microprocessor was something they couldn't really see their way to supporting. So they were looking for ways to share that cost. Apple were not comfortable with using a processor owned by a company they saw as a competitor, albeit a relatively puny one. So setting up the joint venture was very easy for both companies to agree on. But because the launch product from Apple's side was the Newton, then yes, handheld portable was in there from the start. Now, of course, today many people don't even remember the Newton. It was ultimately not a success, but by the time it was becoming clear the Newton was not going to fly, ARM was well established and already branching out. And of course, in the mid-90s, they got the Nokia business. Again, people today don't remember that in the 90s, Nokia was the world's biggest mobile phone handset company, so that was a very big deal. And they really took off in the mobile phone market. But it was the Newton that kicked them off.
Yes. And Acorn did persist with the desktop computers. I know you say you'd left at this point, but they brought out the RISC PC. Yes. So they did push on, but it kind of fell flat. I don't think they ever repeated the success of that BBC Micro in the 80s.
No, I think by the 90s, the IBM PC architecture and compatible machines had basically locked the market into a particular model. And it's very difficult to sell against that well-established standard.
So let's just touch on the legacy then of some of the technology that you've worked on. The BBC Micro first and the Computer Literacy Project. Do you think that combination achieved what it set out to do in the 80s?
I think it achieved far more than anybody could possibly have imagined. I mean, it certainly achieved what the BBC had in mind in terms of its charter obligation to educate the public. But actually, it went much further than anybody could have imagined, partly because of the scale. And of course, the scale was partly because of the BBC logo. In my analysis of the home computer business at the time in the UK was there were lots of small companies, but for the average home user, any one of these looked like a big risk because you'd never heard of the company and you had no idea if it would still be here next week. Whereas when the BBC logo arrived, that was a brand you recognised, and rightly or wrongly, that made you think you could trust this machine or its suppliers to be around a bit longer than the others. And so it became very well established. But I think the thing that more directly addresses your question is the number of people I meet who basically say they cut their programming teeth on a BBC Micro and that changed the direction of their career or set their career direction for the rest of their life. It's still huge, and it clearly slotted into a kind of market where there was a vacuum for this kind of machine, and it seems to have served the people who wanted to learn to do that quite well. I mean, I guess that's something that I'm very pleased about. I mean, it's not clear we knew how to design it to achieve that, so in some sense it wasn't deliberate, but it was a consequence of a number of design decisions, not least putting a rather expensive but high quality keyboard on the machine.
Yes, yeah. Now, I think I saw you mention, it might have been, you did a video at the Cambridge Computer Museum where you sat and watched Microman and gave some commentary on it. And I think I heard you saying that you spent something like 25 or 30 pounds per unit on the keyboard. It was quite a significant cost. Can you remember how much it was?
I'm not sure. Did I say that?
It may have been someone else, but I just remember that figure stuck in my mind.
That number doesn't surprise me, but it isn't a number I have in my head.
Yeah.
It could well be right. I mean, the machine was quite expensive. I think the Model B was $399 eventually, and the retailers sold them for no profit. Okay, interestingly, because they could make a profit on software and peripherals, but the machine itself, the build cost was so tight relative to the selling price that retailers couldn't make a margin on it.
So again, the combination of computer and literacy project, do you think there's a place in the present day to repeat such a project?
Oh, there is, but it will have to be different in nature. I've chaired a couple of Royal Society studies of computing in schools and seen the concern among teachers in schools of the direction the ICT curriculum was taking. and the need to sort of really develop a curriculum where pupils got a much better idea of what was going on, rather than just becoming users, understanding how the machines worked at some level. Of course, that's a lot of the motivation behind the Raspberry Pi, which does seem to have been a huge success in at least part of that market. They've sold vast numbers of Pis, and people use them for all sorts of things. Now, with a Pi, you're still not getting down to the sort of quite to the bit twiddling level of the BBC Micro. You're probably still running Python and using Python libraries to talk to the hardware, but it's getting you much closer to what's going on than is possible, with a PC running Windows, for instance.
And then just coming up to the present day and with ARM again, because it's not just for portable devices. Tell us a little bit about Spinnaker, because I understand that's an ARM-based system and brings us up to the present day.
Yes, I mean, my research for the last 20 years has been focused around the Spinnaker project, where Spinnaker is a compression of spiking neural network architecture. And it really arises out of my experience over the 80s and 90s of computers becoming 1,000 times faster, but still struggling to do things that we humans find quite easy, such as recognizing your mother, which humans can typically do, from a very early age. And we can program computers to do that now, but it's very hard. And so I got interested in seeing where the overlap was between computers and biological brains, and that led through various circuitous routes to Spinnaker. The machine is now up and running in Manchester. We have 1 million ARM processors distributed across 10 standard data center rack cabinets. And this is offering a service under the auspices of the Human Brain Project, which is used by users all around the world. In fact, there are about another 100 small Spinnaker machines distributed everywhere from West USA to New Zealand, also being used. So it's been an interesting machine to build, and it's really my first experience of big machines as opposed to PCs or embedded systems. 1 million processors. The machine incorporates 10 square meters of active silicon area. Okay, so you think of a microchip, and then you think of tessellating these across a wall until you get to 10 square meters. That's how much silicon is running in the Spinnaker machine. And getting all that running reliably has been a real challenge. I've had very good people working with me in the university to deliver on that.
Paul Johnson asks specifically about Spinnaker, and he says, what have you achieved so far with Spinnaker, and what potential consumer benefit do you think that we might see from the work that you're doing with it?
Spinnaker was conceived and developed primarily to support brain science. So fundamentally, it was not intended as a machine that would deliver consumer level results. Of course, brain science is motivated partly just from the interest in understanding the brain itself, which remains one of the great frontiers of science, but also because diseases of the brain cost the developed economies so much money, and of course they affect quality of life of those affected and those around them. And one of the reasons the drug companies have pretty much pulled out of developing new drugs for diseases of the brain is because they don't have models to design those drugs around. So our focus has been on those models. Now, in parallel with the Spinnaker work, there's been this explosion of AI in industry that's now all around us. And we've all got devices we can talk to, and they're using neural nets. But they're not using biological neural nets. They're using artificial nets. And now we're beginning to say, well, what can biological networks learn from the success of artificial nets, and vice versa? What can artificial nets potentially learn from biology? And that's a space where we're now moving into quite actively. Artificial nets are great, but they cost a huge amount of energy and compute to train. whereas biology clearly can learn things on much smaller data sets. If we could understand how the biology works, we might be able to transfer some of that understanding into artificial nets, and then AI would advance. Without those kind of insights, AI is kind of hitting some asymptotes at the moment.
It sounds like a fascinating field. If there's anyone who's listening who wants to follow the progress of Spinnaker or any of those projects, do you recommend anywhere where we can go to read up on them?
Well, if you look at the Spinnaker website at Manchester, there are a lot of papers we've published. I think it's 70, 80, 90 now on Spinnaker. But in fact, we've completed writing a book. I didn't come on here to plug a book, but we'll get a Spinnaker book out within a couple of months. It's with the publisher now, and they're doing whatever final tweaking they do.
Wonderful. I will look out for that, and I'll include some links to the websites as well in the video description. I've just got a few final questions from viewers that didn't really fit in anywhere else, Steve, so I'll just fire these at you. Sebastian Schmidt asks, which research direction would you pick if you were to start going to university today?
That's a very interesting question. I mean, I think picking a research direction has to reflect both your personal interests and opportunities out there. And clearly there are big opportunities in computer science, in AI. So probably if I was an undergraduate now, I would be looking towards AI and deep networks as a space to get into. But if I was more broadly a scientist, then I think there are a lot of things going to happen in the biosciences, some of which will be linked to computer science. So things like gene sequencing are becoming much more accessible. And I think there are major opportunities in the biosciences. If I were feeling really ambitious, I might even look at quantum computing, although my personal take on quantum was it's not going to deliver in my sort of career horizon, and so I didn't really want to work on it. And there are still some reasons for asking questions about where it can ultimately go, but those are exciting areas to me.
Good. I hope that answers your question, Sebastian. The next one's from Julian. He says, do you follow the ongoing developments in the retro community, for example, PyTube Direct, Video Neuler? He lists all sorts of other things, and he says, what are your thoughts on these developments? So do you follow the retro community very much, or are you more of a forward looker?
I don't follow retro very closely, but I do keep coming into contact with it. So I've talked at retro clubs from time to time. I went to a retro computing meeting that was held in Huddersfield, I think probably 4 or 5 years ago, and I must admit I was in a room in the hotel that was absolutely full of BBC micros, and I've never seen so many in one place, for decades. And I was impressed, for example, that somebody built an SD card interface for the BBC Micro, and on a standard SD card, you can hold every program that was ever written for the thing. Of course, it's that's where I learned that the main thing that goes wrong are the capacitors in the switch mode power supplies dry out. If you replace those, it's good for another 20 years or something.
Yeah, and the PyTube Direct, which Julian mentions, is a Raspberry Pi adapted to go into the tube interface and act as a secondary processor on the BBC. So it just goes to prove how flexible, how adaptable that tube interface is, because you then fire up Elite and it's accelerated many hundreds of thousands of times compared to the original.
Completely unplayable, presumably.
Yes.
No, I have played with the Raspberry Pi a bit, and I noted that you can get RISC-OS for the Raspberry Pi.
Yes, yeah.
But I still have an archive of RISC-OS programs from my later years at Acorn, and basically none of them work on the current versions of RISC-OS. So
okay, I've got tucked away here an Acorn Phoebe case, the unreleased Phoebe, this bright yellow case, which was the follow-up to the RISC PC. But of course, the guts of it were never released. So I'm tempted to put a Raspberry Pi in there, but I just don't know what to put in this case.
A lot of space left after the Raspberry Pi.
There'll be, a huge amount of space left. Okay, so Celimax asks, this is again more of a retro thing. He's talking about the Mister project, which is a project to use FPGA to reproduce old computers. So, for example, the BBC Micro has been recreated in FPGA. Is that something that interests you? Do you approve of it? Would you ever be tempted to join a project like that to help out?
Well, it does interest me, and I do approve, but I don't have the bandwidth to get involved in such things at the moment. One of my colleagues at Manchester has had a student project to put a BBC Micro on an FPGA. I don't know quite how that turned out, but I think that there is an important principle here that we do need to try and preserve the software from past ages, and societies such as the BCS Computer Conservation Society have a very important role. Now, mainly, of course, they've been rebuilding old machines such as the Manchester Baby machine, which is a huge undertaking. But if you want to maintain the system and the software, you don't actually need to replicate the hardware at that level. And replicating it on FPGA is probably a much more rational undertaking and probably will survive far longer into the future. And that will enable you to maintain the software. And I think it's quite important that the software is viewed as an artifact as worth preserving as, old Roman masks or whatever. And software that doesn't run is kind of pointless. So we need to find ways to preserve the platforms, and FPGAs provide a very promising approach for that.
Mm-hmm. Yeah, just as important to preserve the logic as it is the software. And I think that extends also to the computer arts, music produced on computers, graphics and art and all of that. I think it all deserves to be preserved. Mark Simpson asks, which single instruction in ARM would you remove and which would you add?
So I don't think there is a single instruction I would remove. ARM's instruction set has some strange features. The conditional execution of every instruction was unusual. And it's very hard to analyze whether it justifies its use of 4 bits in every instruction. That's quite a difficult thing to assess properly. The load store multiple instructions are the ones that really break the RISC mold. On the other hand, they're immensely powerful, and they do give the processor a lot of its performance in terms of procedure entry and exit and so on. So I don't. They were a nightmare to build in, particularly when we decided that we had to support restartable instructions, which was quite a late decision in the development of the first ARM. But I think the thing that I would rework is not an instruction, but it's the way the instructions are put together. I would try to be much more consistent in the fields where the source registers are specified in particular. So in the ARM instruction set, there are 4 different 4-bit fields in the instruction where you can find a source register specifier. And that's too many. It means that to design really fast ARM processors, you have to build register files with 4 read ports, read all 4 of them, and then decide which ones you actually want later. It's too late. You can't decide before because that puts too much logic in the way. So I would take a leaf really out of the MIPS RISC architecture book in that sense. They got this right because it was their second or third go. And on ARM, we got this wrong, and that's incurred a small cost in every ARM since the early ones.
Wonderful, Mark. I hope that answers your question. And then the final question comes from Neil Harris. And he says, did you know BBC Basic made its way onto a Sinclair product in the Sinclair Z88?
No, I did not know that.
There you go. Now you know, thanks to Neil Harris.
Yeah.
So, Steve, thank you so much for your time today, and for all the invaluable work that you've done for us over the years, whether it be as a young student using your creations in school or the phones in our pockets. You've influenced all of our lives in no small way. So thank you very much, sir, and good luck in your future endeavours.
Well, thank you very much. It's a pleasure talking to you.
Thank you.
If you enjoy my content and would like to support The Cave while receiving a completely ad-free experience and access to releases 1 week before they go public, then visit patreon.com/retromancave and join the official Cave Dwellers. Thank you for your support.